All right, so yesterday we talked about pollution in general. Now we're going to start talking about the different types of pollution and how that's classified. So the first lab that we're doing is the porosity permeability lab. Ideally, we would have done it before we did this vocab, but we had the tours this week, so we really couldn't do that. And then the second lab that you have is you have an area and you have to determine where the pollution is coming from and what kind of pollution it is. So we need some of these terms here to figure out what's going on. All right, first things first, point source pollution. Definition of point source pollution, please, Alex. All right, so single source, and on top of that, we know where that pollution is coming from, or we can track it back to that single source. A lot of times that's pretty hard to do. All right, grab a highlighter. Highlight point source pollution. And we're going to give ourselves an example of point source pollution on our little diagram, the Walker-Corey master map. So go ahead and grab that. So we are going to designate randomly, because it's really a bit, but we are going to designate an area of point source pollution coming from the Copper Kettle Company. So the map that we're doing today has nothing to do with the one that we're actually doing in the lab. It just happens to be the same map, the same area, because it makes sense to use something that we're familiar with. But eventually we're going to find out that the Walker-Corey Lake is contaminated. So let's say that after you do that lab, you find out that the Copper Kettle Company has a discharge pipe into that lake. Discharge pipe. And so we can trace the contaminants directly from the Copper Kettle Company into the lake. So whatever color you highlighted, point source pollution. Mine got slipped too. Whatever color you highlighted point source pollution, use that same color highlight to indicate point source pollution that's coming from the Copper Kettle Lake. So you find the contaminant that's in the lake. You find a discharge pipe, you take samples from the discharge pipe, happens to match contaminants that are in the lake, follow the discharge pipe back to where it's coming from, back to the source, point source pollution. All right, next, non-point source pollution. Blake, would you read that one, please? Yes.
Pollution that comes from many different sources, runoff pollution. This type of pollution can be difficult to identify the source.
So you might have several different areas that have the same contaminant, and maybe one of these places is taking care of their pollutants and breaking it down and neutralizing it appropriately, and the other ones have a dump site that's not being taken care of, and so whenever you've got torrential rains, you've got runoff, and it's dumping it into the lake. All right, give yourself a different color highlighter for non-point source pollution. And so now I have a trash dump and road materials and factory waste. And then I've got this stormwater runoff that ends up tracking across the entire area and dumping into the lake. So now I don't know for sure where the contaminants are coming from. So I've got a trash dump. There's contaminants from road materials. There's contaminants from the factory. We've got factory waste. The arrows represent stormwater runoff. And so this represents non-point source pollution.
What does that say right
Road materials, it's an abbreviation for materials. So these both go with point source pollution, non-point source pollution. And so we're going to take the map on. So on your vocab sheet, I've got my little map that I laid on top. I put one little piece of tape right here, and then I opened it up and put a second piece of tape to tape it to that vocab sheet so that it was secure on there. So I laid it on top, one little piece of tape, opened it up, one little piece of tape on the inside. Yep, and put one little piece of tape on this side, then we'll get on there. Alright, next we're going to work from the bottom up down. Biomagnification. Read for us the definition of biomagnification, please, Seneca.
The accumulation of water that succeeds in levels of filtration.
Alright, so now we've got our picture like this. So this is a great diagram so far, but we're going to add a little bit to it. First diagram is water. Let's say that a dot represents a molecule of the pollutant. Got lots of water, so my pollutants can be spread out quite a bit. However, the algae that lives in the area, they're going to take in quite a bit of water within their lifetime, so they're going to take in more than one pollutant. The little critters that eat the algae are going to eat more than one little algae, so they're going to take in more pollutants over their lifetime. The insects that eat the algae then need to eat multiple, because remember our food pyramid, there's only 9% that it gets transferred, or there's only 10%, 90% gets lost. There's only 10% of the energy that gets transferred. And so they have to eat a lot more of the insects that are already holding on to that pollutant. Some pollutants don't stay within the body of the living things, but some do, and mercury is one example of a pollutant that stays within the body. And so these critters aren't affected by it because it's still relatively low levels. Now the fish that eats the insect, that eats the algae that filters through the water and uses the water for its process, well, it's got to eat a lot of insects because it's that next layer up on the food pyramid, and so it's going to have a lot more. Then the fish eat those fish, and so now the pollutants are magnified. And then if we eat those fish, we're kind of like the tertiary consumer, we're on the top level there. So we have to eat lots of fish within our lifetime, and this mercury is being stored in the fish's bodies, and so we end up with tons of pollutant. The mercury levels, the pollutant levels are being magnified with each trophic level of that food chain. Alright, get you a third different color highlighter, highlight biomagnification. Then this goes on the top of the right-hand side. Oh, did you put the vocab on the right? We'll put it on the other side. Okay. On mine, vocab.
Yeah.
Top left of the right page.
You said put it on the top right of the.
This is the right.
Not the, like, this top, that's the
That
top
is
left
your
of the right page.
Okay,
I thought
this is
you
your
said
right.
it was like that right.
I'm so confused.
Just put it on the page next to the vocab. I don't care. Right, left, purple, green. Just tape it in.
Do we need under it?
No, we do not need under it, but next to it, let's add a little information to help us understand what's going on. So right next to it, we're just gonna give ourselves a little information that the mercury levels increase with each trophic level. Mercury levels increase with each trophic level. Alrighty. Next, thermal pollution. Please read for us the definition of thermal pollution, Kale. So there's a lot of factories that are like, hey, we're not putting any chemicals into this retaining pond, into this pond right here. We're not pumping any stuff in there. We're taking water, we're using it to cool off our machinery, and we're putting the exact same water out there. It's not dirty. There's nothing in it. We're not, mixing chemicals with it. We're not dumping anything. The problem is that critters have a homeostasis level. They have a place where it's balanced for their life. So there's a certain temperature difference that they can take. Animals seem to take a lot more of a range, if you will, than humans, because our temperature, we have to kind of modify that a little bit more, it seems to me. But even still, there are too cold and too hot for these critters that are in this pond. And so even if that water is pristine and clean and has nothing in it, it could still end up being a pollutant if, when they dump it into the pond, there are critters that are living in there that can't take that additional heat, that can't take that temperature. More so, the fact that the oxygen is going to be affected. So it's the same thing. It's like a pop. If I have a pop and I put one in the fridge, even with the cap off, and I leave one out on the counter with the cap off on a hot summer day, which one's going to go flat first? The one in the fridge or the one out in the heat? The one out in the heat is going to go flat first. The one in the fridge is still eventually going to go flat, but it's not going to be as fast as the one that's sitting out top. That's why we cool all of the pops down and stuff like that. So hotter liquids can't hold on to those dissolved gases. So the hot pop can't hold on to the dissolved carbon dioxide. The hot water can't hold on to the dissolved oxygen. It ends up evaporating, if you will. It's not really the right term for it. It ends up going back out into the atmosphere. And so that ends up affecting things as well. All right, so thermal pollution. We do have a little bit of information that we're putting underneath here because it's specific. Organisms require specific resources and have a specific range of temperatures in which they can survive. Organisms require specific resources and have a specific range of temperatures in which they can survive. Organisms require specific resources and have a specific range of temperatures in which they can survive. Organisms require specific resources and have a specific range of temperatures in which they can survive. So, any folks go trout fishing? Oh yeah, they're kind of known for that. Salmon and trout, yeah.
Once
Okay.
you put the fish into the, let it, you know,
Oh right, and so they don't put those. I mean, you can't go out to Dow Lake or Hartshorn Lake or Sardis Lake or something like that to get trout, right? Right. You go into Wilburton, you need that nice, cool stream that they have running through there in order to get trout, right? Because they have a specific specific. Is that what I said? They have specific temperature range that they survive in. So you go out to Sardis Lake, even in the hottest of summertime, you can probably still catch bass, catfish for sure. I think you can always catch catfish, can't you? I don't know about crappie. Is crappie temperature like it's pretty much all year long, isn't it? Okay, so you can pretty much go whenever and catch those kind. But trout, you want usually isn't trout season early spring? Is that when you went? Early spring when it's cooler out.
yeah.
All right, so they have a specific temperature range that's best for them. So rainbow trout are extremely sensitive to temperature changes. So if you're sensitive to temperature changes, your choices are adapt, migrate, or die. Lovely, right? Adaptation is obviously the great because then you can stay where you're at. The problem is adaptation takes a while. It takes generations to do that. Migrate is nice, but if you don't have bodies of water that connect to each other, how are you going to get from one place to another? So in some situations, it just dies off. Additionally, if we have an increase in temperature, warmer water makes it ideal for the plant life or algae or plant-like protists. And then if we have an increase in the algae, that's that algal bloom. That's the huge, very quick producers that are all of a sudden present. And that can lead to eutrophication. Rainbow trout are extremely sensitive to temperature changes, so their choices are adapt, migrate, or die.
You die from it.
I choose to die. Adaptation takes a while, it takes several generations at least. Migration, you have to have a path, you have to be able to migrate. An increase in temperature can equal an increase in algae, plant material, and so that can lead to eutrophication. All right, what is that, our fourth different color highlighter? Highlight thermal pollution, box in our thermal pollution information. All right, last vocab term for today, artificial eutrophication. Can you read for us that definition, please? Rachel.
An unnatural overabundance of nutrients within an aquatic ecosystem from fertilizer or sewage runoff dissipates in algae
An algal.
algal bloom. When the algae die, decomposers use up the oxygen to break down the algae. Other aquatic organisms suffocate because their water is oxygen
depleted. All right, so the first time we saw it, it was natural, and it does happen naturally. This time it's artificial. So artificial usually is key, or it usually leads back to humans. So at the very bottom, you have two post-it notes, and you might recognize these two chemicals, these two substances. We touched on it on that Kahoot the other day. Phosphates, phosphorus, nitrates. Phosphates, phosphorus, and nitrates. These are two key substances in our waste products that end up causing artificial eutrophication. It will if you look at a bag of fertilizer. I mean, those are going to be high potassium, phosphorus, nitrates, I want to say. And I haven't looked at a bag of fertilizer in a long time, but chances are there's going to be certain percentages of those things that are in there. So yeah, they love that stuff. One critter's poop is another critter's fertilizer. All right. Phosphorus. We need phosphorus. We need phosphates. That is absolutely crucial for us to create our ATP and to create our DNA. It comes from rocks. The source that we get it from is from rocks. If we had done our phosphate cycle like we did water, carbon dioxide, nitrogen, and maybe that was it, water, carbon dioxide, nitrogen, we'd see that that's the source of phosphates. We need phosphates. We cannot survive without phosphorus. The bad part of phosphorus is that if it's in untreated sewage, then it's going to cause, be part of runoff, and it's going to cause the artificial eutrophication. Because it's part of fertilizer. If you don't use the fertilizer correctly, if you do it right before a big rainstorm, it can be part of runoff. Even our detergents, the soaps that we use, they're high in phosphorus. And so just by us taking a shower, we're dumping that into the environment. So phosphorus is essential. We need it for ATP and DNA. Comes from rocks. Of course, when we get it, it's because of the breakdown of rocks and it gets into plants. They absorb it or into the water supply. Bad part is that it is part of untreated sewage, fertilizer, and detergents. And so those kind of runoffs end up polluting aquatic ecosystems. All right, nitrates. Nitrates are essential. We need nitrates. They're used by the body to dilate blood vessels and to help us regulate our blood pressure, especially lower our blood pressure, because your blood pressure is regulated throughout the day. And that's just one example. The bad part is, once again, it becomes part of fertilizer runoff and untreated waste, sewage in the septic system. If it's not treated correctly, it becomes part of the problem. So used by the body to dilate blood vessels, lower our blood pressure, fertilizer runoff, sewage, and septic systems. So nitrates can be part of the problem if they're not processed correctly in fertilizers and in waste products. Used by body to dilate blood vessels, that helps to lower blood pressure. Nitrates are bad for the environment because they can be part of the pollutants in fertilizer runoff. And if it's left untreated in sewage and septic systems, then they can pollute the environment. All right. that's all I have for you today. So sorry that we're ending early. I know that you just want to go through the, I know. Wipe those tears. Yeah, so that would be what, your 5th different color highlighter? So you highlight artificial eutrophication, and that's what that should be highlighting. So mine was supposed to be blue, but can't handle that apparently. Alright, that puts us in a good place for next week. You not didn't? Okay. Well, yeah, but I mean, I can do it on you.
This is my favorite part.
Oh, okay. Oh, I thought you were like, oh, she didn't.
No.
My favorite part of it
Is to get candy.
yes. I'm not even going to lie.
There's got to be some sort of reward for it.
I like reading.
You like reading?
I'm definitely up for about read all the definitions in case we follow them. I've already went over them.
You've already done them all.
Yeah, I really